let's take a look at problem 8. So this is asking us about Rolle's theorem. 6 and 7, I did have you write down Rolle's theorem and mean value theorem, so you would remember what was what. You always have to start with the criteria. Okay, so Rolle's theorem has 3 criteria. It has to be continuous, which it's a polynomial, so it is. It has to be differentiable on the open interval, which polynomials are always differentiable. I'm writing out the specific definitions, but if you just said it's polynomial, so continuous and differentiable, that's totally fine. The third criteria is that the endpoints have to be equal. So these are 2 x values. If you put in a 1, you get 5 minus 12 plus 3, so negative 4. If you put in a 3, you get 5 minus 36 plus 27. Their endpoints have to be the same. If they are, then we can do Rolle's theorem, which says that somewhere the derivative is equal to 0. It's really kind of the same thing, it's just a special case of the mean value theorem. Remember, mean value only has the first 2 criteria, and then it says somewhere the derivative is equal to the slope between the endpoints. If the y values are the same, what's the slope between the endpoints? 0. So it's just a special case of that. So we do our derivative. And then because Rolle's theorem says somewhere it's going to equal 0, and we get 2. You might get multiple values. Your answer is only the one that's in the interval between 1 and 3. So number 9 is asking us about mean value theorem. So we have our criteria first. And there's only 2. Polynomial, so it is continuous on negative 2 to 2. It also has to be differentiable. So again, because it's a polynomial, it is differentiable on the open interval as well. You could have just said it's continuous and differentiable everywhere because it's polynomial, totally fine. Then, mean value theorem says that somewhere the derivative is equal to the slope between the endpoints. So we need the slope between the endpoints. So if we put in a negative 2, negative 8 plus 6 plus 2 gives us 0. If we put in a positive 2, 8 minus 6 plus 2 is 4. So the slope y2 minus y1 over x2 minus x1, and we get 1. So we know that somewhere the derivative is going to equal 1. So our derivative, 3x squared minus 3 equals 1. So 3x squared equals 4. So x squared is 4/3. To get rid of a square root plus a minus. Square root of 4 is 2 over the square root of 3. Get the radical off the bottom, so plus and minus 2 radical 3 over 3. If you verify, both of those do fall between negative 2 and positive 2. So we have both. Any questions there? Problem 11. We want absolute and local max and min for this graph. You can write these in function notation or as ordered pairs. Okay, so your absolute max is the highest on your entire graph, so that's happening right here. So my 4. So we get 4, 5. Okay, my min, the lowest on the entire graph, that happens right here, but when you look at it, what kind of circle is that? It's open, so it doesn't count, so we can't say the lowest point, so there is none. Local max, those are higher than the points on both sides of it. It can't be an endpoint because there has to be points on both sides. So when I'm looking right here, this would be one, but it's open. But what would this point right below it be? A min, because isn't it lower than the points on both the left and the right? So we have a local min at 1, 3. Okay, if I'm traveling along right here, this point is also lower than the points on both sides. So that one is at 2, 2. This one, it was my absolute max, but it is also a local max because it's not an endpoint. So 4, 5. Okay, traveling along this one right here, it's lower than points on both the left and the right, so it would be another local min. So that's at 5, 3. Okay, this one right here, there's a break in the graph, but it's not the endpoint. There are points on both the left and the right, and it's higher than both of those, so that makes it a local max. That's 6, 4. Number 12, the absolute max and min. So first we have to find our critical points. Critical points are anywhere the derivative is 0 or undefined. So if we do the derivative, the 1/3 comes down, inside stays the same, subtract 1 from the power, times derivative of the inside. So you could write this as 4 over 3, a negative 2/3 power, that's the cube root 4x plus 8 squared on the bottom. If you set this equal to 0, you would just multiply over the bottom and have 4 equals 0. So that doesn't happen. But critical points are anywhere at 0 or undefined. It would be undefined if the denominator is equal to 0, which is really just when 4x plus 8 equals 0. So negative 2 is our only critical point. So then we have to check our 3, negative 5, 0, and negative 2. Sometimes you might get multiple critical points. You only check the ones that fall in the interval. So even if I gotten like a positive 2 as well, I wouldn't use it. All right, so if I put in a negative 5, this just means the cube root 4x plus 8. So if I put in negative 5, negative 20 plus 8 is negative 12. So I have cube root of negative 12. It's probably, I don't know exactly what that comes out to be, something between negative 2 and negative 3. If I put in 0, I get out the cube root of 8, which is 2. If I put in negative 2, I get out the cube root of negative 8. Or sorry, the negative 8 plus 8 is 0, so cube root of 0 is 0. So then we can see this is my lowest, so that's my absolute min. And 2 is my highest, so that's my absolute max. So absolute max and min, I would have to give you an endpoint. So you find all your critical points, you test those and your endpoints to find the highest and lowest. Any questions there? Number 13. does there exist a polynomial where f of 0 is equal to negative 1? Okay, that's just like giving you a point. 0, negative 1 is a point on the graph. F of 2 is equal to 4. And the derivative is less than 2 for all x's. Okay. Can't really tell much from our graph, can we? We do know it's a polynomial. By telling you it's a polynomial, what have I told you? Yes. All right, so we know it has to be continuous and differentiable. There's no breaks in this graph, derivative always exists, no corners. If it's continuous and differentiable, then the mean value theorem has to work, right? So the mean value theorem says somewhere the derivative is equal to the slope between the endpoints. I gave you 2 endpoints. y2 minus y1 over x2 minus x1. So we get 5 over 2, or 2.5. So by the mean value theorem, f prime has to equal 2.5 between 0 and 2. So this is not possible. The derivative can't always be less than 2 because mean value theorem tells us somewhere it's going to be 2.5 in that interval. Kind of like we talked about, in terms of driving. Like, is it possible to drive to Hannibal, have an average speed of 65 miles per hour while you were always driving less than 60 miles per hour, or less than 65? It's impossible. You had to at some point hit it. Is that okay? Right. Problem 14. So our function is 1 minus x to the 2/3. Show that f of negative 1 is equal to f of 1. So if I put in a negative 1, this is the cube root of negative 1 squared. So we get 0. If we put in 1, we again get 0. Okay, but there is no number between negative 1 and 1 where the derivative is 0. If I do this derivative, we get negative 2/3 x to the negative 1/3. Negative 2 over the cube root of 3 times the cube root of x. If you set that equal to 0, you get negative 2 equals 0, which can't happen. So I want to know, why does this contradict Rolle's theorem? Rolle's theorem says if the endpoints are equal, the derivative has to equal 0. But we just showed the endpoints were equal and the derivative is never 0. Yes. This doesn't meet the criteria. It's not differentiable when x is 0. That's undefined right there. So I really just put these last 2 questions on there to make you think about what Rolle's theorem and mean value theorem say. This one especially to illustrate why we have to verify those criteria. It only works in certain conditions. If the criteria aren't met, then it doesn't have to be true. Is that okay with everybody? And then number 16. All right. In each part, state the x-coordinates of the inflection points of the function. Give reasons for your answer. So if this is the original function, this is the graph of that, tell me where the inflection points are. Inflection points are where the concavity changes. So this graph starts off concave down, now it's curving up, so somewhere in between we had to change, right? So 3. It's curving up, but now it's curving down, so somewhere in between we change, so maybe 5. Okay, and it stayed curving down. Is that an exact science? No, but I think those are pretty good estimates of where it happened. All right, second one says, if this is the derivative. All right, so now we have to think. I can't just look at this and say where the concavity is changing. I want to know where are the inflection points if the graph I'm looking at is the first derivative. So remember, inflection points are when the second derivative is equal to 0. If I'm looking at the first derivative, I'm saying when will the derivative of this be 0? So that's anywhere we have a horizontal tangent line. So that would be here, here, and here. So we have to think about the relationship between all of these things. So if I'm looking at the first derivative, I know the second derivative will be 0 when we have a horizontal tangent at a max or a min. The last thing, if I'm looking at the second derivative, then the inflection points are when the second derivative is 0. So it's 0 here, here, and here. So 1, 4, and 7. And the reason is just that it's equal to 0 there. Kind of organize it for you a little bit to make it easier if you're trying to look over some things and review before this test tomorrow. Make sure you know your criteria for mean value theorem and Rolle's theorem. The Rolle's theorem, what's the first criteria? Second criteria? And the only difference is it doesn't have to be differentiable at the endpoints. It does have to be continuous there. And the third criteria? So f of A is equal to f of B. And then the result, if those three things happen, the derivative equals 0 for some x between A and B. All right. Mean value theorem is more generic, so it has fewer criteria. It's only the first two criteria. It's continuous on the closed interval, differentiable on the open interval, and there is no third criteria. Then what does it tell us? The derivative is equal to the slope between the endpoints. For some x between A and B. All right, so make sure you know those two theorems. Those will probably be a couple multiple choice questions on your test. Have to know your criteria and then the result that it says. All right. Then let's talk about the difference between critical points and inflection points. Critical points are when the derivative is what? 0 or undefined. And these are points where you have local maxes or min. What are the inflection points?
Second derivative. 0.
Good. And these are the points where the concavity changes. How do you find absolute maxes and mins?
Critical points.
Mm-hmm.
Extra critical points.
Good. We find the critical points, critical points and endpoints into original to get our y values. If I say plug them into the original, do you know what that means? Then the highest y is your max and the lowest y is your min. So then, when we get into the graphing, sometimes we're having a little bit of trouble graphing. So I just put like a couple conditions. Can you draw what that little section would look like? What would it look like if a graph is curved upward but increasing? Yeah, something like this. If it's curved downward but increasing, that just changes it. So it's kind of like getting ready to form an upside down parabola. Okay, curved upward but decreasing. So decreasing just tells me it's falling. Or it could be curved downward and decreasing. So those are really the 4 different shapes. We look at increasing and decreasing, whether it's rising or falling, and concavity tells us how it's curving. Vertical asymptotes, what do the equations look like?
Move the denominator closer.
Yes. So it's always going to be x equals a number where denominator equals 0. Okay, horizontal asymptotes. What are those? How do we find those?
Limit y approaches with the function which is negative and positive.
So those are always going to be y equals a number. As x approaches positive and negative infinity for our function. All right, so those boxes there really just summarize all the content. Like, you have to know what those things mean or how to find those things. Are there any questions there? The last few two have graphs. because I know these were a little bit harder on the study guide, but they're really good questions for making you think about how everything is connected. So I thought we might try a couple more of those. All right, so this first one tells me if the graph of f of x gives the x value, consider the graph, okay? If the graph is f of x, so this is the original function, give the x values of the maxes and mins. So I'm looking at the function. Where does it have a max? Yep, and I only asked for the x values, so you don't have to, if you gave me the order pair, I certainly would not count off, but you only have to tell me the x. Are there any other maxes? No, that's it. So my min, where do we have minimums on this graph? Okay. And what would we call the other one? 2.8-ish?
Yeah.
All right. Where would we have inflection points? So that's asking where the concavity is changing. If I'm looking at the original, it's curving upward, but then we switch and we're curving downward. So the question is, where does it switch? You're usually just kind of looking for the middle here. Best guess, -3 looks good to me. And where else? Now it's curving downward, but there it's curving upward. 1. All right. So those are those questions okay there? That's what we're used to thinking. We look at the graph, we're identifying this. Now I'm going to try to switch how you think about it. If the graph is f prime, so I am looking at the derivative already, where would the maxes and mins happen? All right, think about this. When we find our maxes and mins, that happens at critical points, right? So when I'm looking at this, my critical points are anywhere this is 0 or undefined. So we have 4 of them here. Now you don't have to write out a sign line, but I'm going to illustrate something here. So our first derivative is 0 at -6, -3, 1, and 4. So those are the places that could be our maxes and mins. If I look before that, my graph was positive. After that, first one it's negative. After 3, it's positive. Here it's negative, and then it's positive again. If you go from positive to negative, that means our graph went from increasing to decreasing. What happens at -6? Max. This is kind of hard to think about because we're wrapping our mind around the fact that I'm looking at the graph of the derivative, not the original function. Okay, when I get to -3, my derivative went from negative to positive. That means the original went from decreasing to increasing. So what happened at -3? Okay, at 1, my derivative went from positive to negative. That means the original function was increasing, then decreasing. So 1 is a max. Alright, and then at 4, we went from negative to positive. That means the function went from decreasing to increasing. So 4 is a min. The inflection points. If I am looking at the derivative, inflection points are when the second derivative is 0, right? If I'm already looking at the first, I'm asking myself, when will the derivative of this be 0? So I'm saying, where do we have horizontal tangent lines? here, here, and here. So negative 4.8, negative 1, and positive 2.8. Other questions on that graph? Why don't you guys take a minute and try the next one? I apologize, the graph isn't as pretty. I was trying to draw one and it's not great, but see how we did. Not all these were nice x values, but we can probably get close. So our max. If this is the original function and we have a max at negative 3, probably positive 1/2, and positive 4. My mins, my low points, can't include endpoints. So negative 3/2 or negative 1.5. And positive 3. Did you get those? Inflection points, we're going to estimate as best we can. So it starts off concave up, or concave down, switches to concave up. So you're estimating where that change happened. It's not perfect, maybe somewhere around there. So maybe a negative 2.25-ish. Here we're curved up, and then we switch to curved down, so it does change again. So I don't know if you want to call it maybe negative 1-ish. If you had called the first one negative 2 and the second one negative 1, that's probably also okay. It's really hard to tell on this graph. We're curving downward, switch to upward, so it looks like we change where? About 2. And we're curving upward and switches to curving downward, so maybe 3.5. All those are ballpark, so if you're close, and it's fine. Are those okay? All right, now this is where the challenge is. Switching, so we are thinking about this differently. If what I'm looking at is not the function, but it's instead the first derivative, where would we have maxes or mins? So the first derivative is here. Maxes and mins happen when that first derivative is 0. So we can see it's 0 here, 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 and here. So we're going to have 4 of them. All right, I don't have anything before this. So can I count, oh, hold on, I'm doing, okay. So if I'm looking at this one, at my negative 4, can I count that as anything? No, because it's an endpoint and local maxes and mins can't happen at the endpoints. So the first one we can look at is the negative 2 right here. So if you need to, you could draw yourself a sign line. You don't have to. So before negative 2, my graph was positive. After, it became negative. And we went positive and negative. So that means the function was increasing and then switched to decreasing. So negative 2 would be a local max. Negative 1, it went from negative to positive. So it went from decreasing to increasing. So negative 1 is a local min. At 2, the graph went from positive to negative, increasing to decreasing. So 2 would be a local max. All right, inflection points. Inflection points happen when the second derivative is 0. So if I'm looking at the first, I'm asking when will the derivative of this be 0? So that's at these horizontal tangent lines. So if we give all of these x values, we've got probably -3, -3/2, +1/2, +3, and +4.